Today we're talking about similar polygons, and so we are reminding you of this, which we saw back earlier in this packet of notes on day 2. Two polygons are similar if they have these two features. All right, first of all, corresponding angles are congruent, and corresponding side lengths are proportional. We spent day 3 talking about proportions and cross multiplying, and we'll see that from time to time moving forward as well. And so what that means is we need to compare the corresponding sides. We also need to compare the corresponding angles, and that's what we're going to be doing in these examples below. Here's a new symbol, and that means similar. So if we're going to say one triangle is similar to another triangle, or one figure is similar to another figure, that's our symbol for similarity. It looks like the tilde sign. It looks like what you see on top of the congruent sign, but without the equals underneath it. All right. So this is just more of an informal observation with these two triangles here by using the tracing paper just so that we can compare those corresponding angles, because we don't actually have numbers printed to be able to compare the degree measurement. So if we were to take triangle ABC and reposition that so that it's on top of the other triangle. They're obviously not the same size, but you can take a look at those angles and observe that, yeah, angle A is the same size as angle D. So they're corresponding and congruent. Notice if we were trying to like rotate angle A and put it up here on angle E, those would not be the same size. So we're looking at angle B now, and angle B does seem to be the same size up there at the top. So that's a second pair. And then we check the third pair. There's angle C. It pairs up with angle F. So it's not a formal proof, but it is an observation. And so are the corresponding angles the same measure? We would say, are they congruent? Yes. Now, is that enough for the triangles to be congruent? No. We know that congruent triangles have to be the same size and the same shape, and they're clearly not the same size. This one is bigger. So when you're looking at those side lengths, you can see that we're consistently bigger. 10 to 15, 8 to 12, 12 to 18. So yes, they're bigger, and in fact, we're going to analyze those side lengths in the next part here in just a moment. But in general, we appear to be scaling up, or if you go this way, scaling down. So they appear to be proportional, but we haven't proven it yet. So I'm going to take a look at step number 2. So let's check to see if the ratios of corresponding side lengths are equal. So this tells you the ratios to look at. So this is AB, which is the upper left side, and DE, which is the upper left side. So we're comparing 10 to 15, and then we always reduce the ratios. We can divide out a factor of 5 from top and bottom and get 2/3. So the next pair of sides is the upper right side. So we have 8 to 12. And that reduces to 2/3 as well. And then the bottom side, CA is 12, FD is 18. That also reduces. We can factor out a 6 from top and bottom when we get 2/3. So notice we get the exact same result every time. This 2/3 that you see is what we call the common ratio, because the common ratio is common to each pair of sides. So that helps us to kind of see a little bit more clearly that, yes, these side lengths really are proportional. I should say the corresponding sides are proportional. And not only do we have a common ratio of 2/3, but it's also going to be the scale factor. Now you might ask yourselves, wait, is the scale factor supposed to be 2/3 or 3/2? And in general, it depends on the order that they state the names of the triangles, or in this case, the position. We're going from left to right. So that we're saying for every 2 units of length on this shape, there's a corresponding 3 units of length on this shape. So we're saying 2/3 is our scale factor. But if we were to go the other direction, we would change it to 3/2. And we'll see some examples of that where we're setting it up to help find missing sides. In this case, we don't have any missing sides. So this phrase here is called a statement of proportionality, right? So this is a ratio, this is a ratio, this is a ratio. But if you take this ratio and you set it equal to another ratio, that is a proportion, right? So what we're saying is this ratio of these sides set equal to the ratio of this sides, that is a proportion. Now, of course, we have 3 pairs of these sides. So instead of writing 3 ratios independently, we just group all the ratios together so that we have a long proportion instead of 3 separate proportions for each pair of ratios. So this is the third ratio. So what you're really saying is you can compare the first and the second ratio. There's a proportion you can cross multiply if you had to solve for a missing side. Or you can cover up the middle ratio. There's a proportion, and you could cross multiply there to solve for a missing side. Or you could cover up the first ratio, and there's a proportion, and you could cross multiply here to solve for a missing side. So we're just grouping all of the proportions together to make one long proportion. We call that a statement of proportionality, because a proportion sets one ratio equal to another. And again, we've already identified the angles visually with the tracing paper. Angle A is congruent to angle D. Angle B is congruent with angle E. And lastly, C with F. So what we're doing is we're checking to see if those corresponding angles are congruent and if those corresponding side lengths are proportional. So yes, we do have a common ratio. Yes, we do have those pairs of corresponding and congruent angles. So we would say triangle ABC, there's a new symbol, is similar to triangle DEF. We'll see another shape on the back side, but first, have you heard of these words? The altitude is the same thing as the height, and we deal with heights all the time, and you know the heights are always perpendicular to the base, and that's what this is saying. It's a segment from a vertex, there's the vertex at the top, perpendicular to the opposite side. So there it is, perpendicular to the base. So what's interesting is if you were to draw an altitude for each vertex to the opposite side, and here I'm freehanding it so it's not real precise, but if you were to draw it precisely, it would in fact result in a common point right there. We used to study this more in detail in past years. We don't so much now. But there you go. You have altitudes. We also have medians, and a medians is another kind of segment that goes from a vertex, but it's not perpendicular. It goes to the midpoint of the other side. So if I were to just kind of eyeball where I think the midpoint is on the other side, there's a median. You can see it is not the same as the height because it's not perpendicular. Well, if I were to identify the midpoint on each side and then draw the median, then, again, I'm just freehanding it here. Might be a little bit rough, but it should result in that similar pattern where you end up with one common point. All 3 medians cross each other in one common point. That's the middle of your triangle. And the same way that all 3 altitudes cross as well. So the reason why we're introducing these words is because not only will we find that the corresponding sides will have a ratio, we can also compare the corresponding altitudes, the corresponding heights. So for example, if you had a height on this triangle and a height on this triangle, you would find they also are in the ratio of 2 to 3. Or you could compare the corresponding medians, and if you compared this median to that median, it would also be the ratio of 2 to 3. And that's what we're going to look at more closely in the next example. So it's formally described here in this box. Here it says corresponding lengths, so that could be on the sides or it could be on the inside with a median or with an altitude. So if 2 polygons are similar, then the ratio of any 2 corresponding lengths, right? So that could be your altitude or your median. Any 2 corresponding lengths in the polygon will be equal to the scale factor. So let's take a look at that concept here in example number 1. Here we have similar triangles, and they tell you JKL is similar to EFG. Again, the order of the letters matters. So, for example, if you look at the first two letters, J and K, and compare that with the first two letters E and F, those are your corresponding parts. We're not saying they're congruent. Remember, they're going to be proportional, but this side will pair up with this side over here. Our goal here is to solve for the median, the length of the median KM. So this is what we want to find. This is our variable here. And we have the median on the other triangle, which is 10. All right, so we're going to use the scale factor. We're going to use this proportion to help us figure out the length of this median on the larger triangle. Now, when you take a look at this particular side from J to L, all right, so J and L are the first and third letter, so that would pair up with the first and third letter EG. You can see that, yes, we have a midpoint. That's what a median is. You got your tick marks there. This is 48. This is also 48. If this is 40, this is also 40. We could add up the pieces and make a large total of 80 for the entire length of that triangle. We could, again, add up the 48s here and get a 96. But we're not going to, because this idea is that we could use any two corresponding lengths, even if that means part of a triangle side. So we're going to compare part of this triangle side to this triangle side, part of this triangle side, and compare this median to this median. So let me write what that proportion would look like, and then we'll plug it all in. So we're saying this segment from J to M is proportional to this segment, HG. And that will equal this median, KM, to this median, HF. All right, so that's the concept here. So let's plug in our values. JM is the 48. HG is the 40. KM is unknown. That's the variable. You could use X or Y. I'll just call it KM. That's the variable. And HF is the 10, right? So that's the idea, and then we're going to cross multiply. So 40 times the variable of KM equals 48 times 10, so there's 480, right? And then we'll divide both sides by 40 to get our variable by itself. So let me divide both sides by 40, and my result here is, turns out to be 12. All right, so that's what we're saying. You can use the entire side length of a triangle, and oftentimes we will, but in a case like this, we could even use part of a triangle side length. And we can do that here because both of them are half of the total side length because we know we have midpoints. All right, so recall this as well. If the corresponding sides have a common ratio, then that is also the scale factor. So let's talk about that in the next example. All right, so instead of triangles, we have quadrilaterals, but we're just showing you that we still have to check both angles and sides to see if we have similar figures. We want to determine whether these polygons are similar. If they are, write a similarity statement and find the scale factor from, notice here's your order. They're telling you ABCD first to JKLM second. So whatever is first will go on the top part, and whatever is second will go on the bottom part of your ratio, of your fraction, of your scale factor. So information from ABCD will go on top, and information from JKLM will go on the bottom. And we'll see that here in the ratios. Okay, so first, the angles. Angle B has a single arc that pairs up with the single arc at K. C with the double arc pairs up with angle L. D with M. And then, of course, we know that a right angle is congruent to a right angle, so we know angle A is congruent to angle J. So, yes, all of the corresponding angles are congruent. Now we have to check the side lengths. All right, and so again, this is guiding us here. So AB and JK, so AB is 8, JK is 14, so 8 and 14. Notice the pattern. Information from ABCD is going on the top. There's the length AB going on the top. And then we can reduce that by 2, right? So that'll give us 4/7. Next, AD is on the left-hand side, so 12 and 21. And that can be divided by 3, giving us 4/7. Okay, so far so good. We have a common ratio so far. Let's see, CD is 8 over LM, which is 14, so it's another 4/7. And lastly, this one will give us the right-hand side, which is another 8 over 14. So again, 4/7 there. So yeah, look at that. We have a common ratio. So there it is. When it says circle the common ratio, we got it. And the ratios are equal, right? So the corresponding side lengths are proportional. That means you could set this ratio equal to that ratio, and that would be a proportion. Or you could set this ratio equal to that ratio, or this equal to that ratio. And you'd get lots of different kinds of proportions. So ABCD is not a triangle, so we don't get that little symbol in front. It's not a parallelogram. It's just a quadrilateral. Is similar to JKLM, right? And the scale factor is 4/7, right? So remember that information about the first shape is going on the top, information about the second shape listed is going on the bottom, and it should match your common ratio as well. So what this is saying is we're saying that for every 4 units of length that we find in figure ABCD, there's a corresponding 7 units of length in figure JKLM. And that kind of makes sense. If you look at the picture, like the top side, for example, for every 4 units of length, there should be a matching 7 units in the other figure. So if this is 8 units of length, that means you have one set of 4, here's another set of 4, there's 2 sets of 4. So that means you should have a corresponding 2 sets of length 7. Yeah, 7 and 7 make 14, just like 4 and 4 make 8. There's 2 sets of 4, there's 2 sets of 7. So this is what we're saying. Every 4 units in the first shape corresponds to 7 units of length in the second shape. Here's another set of 4 units, and here's another set of 7 units. So let's finish off with this final example here. We're going to find the common ratio, which is also the scale factor, and then solve for the missing side. And again, notice whatever comes in front will go on top, and this will go on the bottom. So FGHJ, that's this shape here on the left. I'll put this information on the top. So we have lots of numbers to pick from. We could pick this upper left with this upper left. We could pick the left side with the left side. We could pick the bottom side with the bottom side. But you want to pick 2 sides that have numbers so we can set up a ratio. And I guess I'll pick this upper left side. So that's what I'm highlighting here, just so you can see I'm looking at that. I'm going to use FG and LM. All right, so that means we have a ratio of 15 over 12. Now we always reduce our ratio, so that'll give us 5/4. So that's the common ratio, but it is also the scale factor. So when we find the value of x, we can use that scale factor to build ourselves a proportion so we can then cross multiply. And what we're doing now is we're pairing up a pair of sides, one of which includes the variable x, because that's what we're trying to find. So we have to use the right-hand side, so that'll pair up with the 40. So again, 40 belongs to the shape FGHJ, so that has to go on top. So we'll put the 40 on the top, we'll put the x on the bottom, and then we can cross multiply. Now technically you could have also used the 15 over 12, right? You could have done the same thing and used this 15 over 12 to set up a proportion and cross multiply. But the scale factor is nice here because the numbers are smaller, so it's a little easier for us to do our work. All right, so we have 5 times x equals 40 times 4, and then we'll divide away the 5, and that'll get us a result of 32.